Good afternoon, physics class, and happy Monday. This is Mr. Thompson, video version of our lecture for today. We're going to be looking at understanding how sound is created and transmitted. We're going to start with the entry task question that's up there. The speed of light is 3 times 10 to the 8th meters per second. Red light has a frequency of 400 nanometers. What is its frequency? Take a minute and try this out. If you have specific questions as you try this, you may put those in as your entry task, but I'd like you to try this out right now. Take a few minutes here in class and then post that in the comment section for this video or for our online meeting. Before getting to the entry task, please note that your homework is to read this section for today. There are a set of book problems on chapter 26 I'm going to have due Wednesday, so you're welcome to read ahead, but to keep things consistent, make sure that they're done by the end of our time in class on Wednesday. I think I put it as 10 o'clock in the evening. Just scan that image right up there. Thank you for all those who've turned in assignments on Teams. Please be checking those. I've gotten those back. If you are missing something or if you have a question, communicate on our team site, or if it's an individual thing, you can also tell that to me directly. So if we look at solving this question, please note I put the wrong color down. This should be purple is what I meant to say, but same numbers. So if the purple light frequency is given, we're being asked for, given its wavelength of 400 nanometers and a speed of 300,000 meters per second, which is our value for the speed of light. So in this equation, we're using our given velocity of a wave. Any wave is equal to the wavelength times the frequency. We want the frequency, so I'll rearrange that equation to say that the frequency is going to be equal to the velocity divided by the wavelength. You plug in your known numbers. Now, this is all math problems. Practice this out a couple different ways and see if you understand it. 300,000 written as a scientific notation would be 3 times 10 to the 8th meters per second. This is a constant in a vacuum for the speed of light. And the wavelength then of 400 nanometers. So the prefix nano means times 10 to the negative 9th. You're welcome to look that up. It's not something to memorize, but do want you to know how to use it. So 400 times 10 to the negative 9th meters. So before plugging this in anywhere, first just look and see what would make sense. You've got a very large number up here. There, this is very big, and this is very small. Remember the negative value, if I was going to draw out 400 times 10 to the negative 9th, it would be 400, and then you take the decimal, move it 9 places to the left. 1, 2, 3, 4, 5, 6, 7, 8, 9. So this becomes, that's how many meters? 0.0000004 meters is 400 nanometers. So obviously those aren't the real distance, but that's my wavelength that I'm looking at right there. So big number divided by a very small number, we'd expect a very large number. What should its units be in? Remember that when we do these calculations, we're looking to find for frequency a measurement of a number per second, also given as the value of hertz. So meters would cancel. I'm left with seconds on the bottom of the equation. So when I plug this in, test this out, online calculator, Desmos, whatever you want to do, you should get a very big number of 7.5 times 10 to the 14th. My units are still over seconds, so number over seconds, which can also be written as 7.5 times 10 to the 14th hertz. That's my value for the frequency of this purple light. Reminder then, you had some homework problems on this concept in general for waves. Make sure that is in. That was due at noon today. So if you don't have that in yet, get that in soon. So a little bit about sound, what it is. We're looking at sound and vibration. And the origin of all sound is vibration of objects as they move and they create a pulse in the air. So some different examples of sound: strings, a stringed instrument. It could be a rubber band that you pluck, it makes a sound. So strings can cause that. The mouthpiece of an instrument, say the oboe, or any reed instruments, they vibrates that piece of reed. Also the soundboard on a guitar kind of does both those things. It vibrates the string, but also the wood piece there. Your vocal cords, as you listen to me talk or as you talk to somebody else, it's the vibration of cords in your throat that produce this vibration. A piece of metal, anything that is moving the air around it is going to create a sound. We describe then our impression of sound with the word pitch. So high pitch means it's got a high frequency. Low pitch, it's got a low frequency. And on the next page, I've got some things on this here, but this is one that's easy to play around with. I know I talked about it last week, but get an app or something like that that allows you to change this and to hear what that sounds like. So a young person your age can usually hear frequencies up to 20,000 hertz. As we get older, and I will include myself in that, this shrinks a little bit. So if you try this out, especially if you start at 20,000 hertz, as I tried this out here this morning, I put a link. I believe I put a link in your description in the team site, but you can also look up a number of these things. Try starting out at 20,000 hertz and see what people around you notice it. My dog definitely noticed it here as I'm recording this, as he was looking around to see what was causing that noise. I could not hear it until I got down to about 17,000 or so, depending on your app and how loud it is. But that's typical as you get older, that hearing shrinks at the high frequency end. So go ahead and try that out. Find something like that. There's a lot of apps on your phone that can do that. Be helpful to understand these concepts as we move forward. A couple different terms. The word infrasonic are sound waves that are below 20 hertz, so very, very low, and above that are called ultrasonic. And certain animals, like I mentioned, dogs and others, can hear way above human hearing capability. So the word dog whistle, a dog whistle is one where the frequency is quite high, well above all human hearing. So you blow it, doesn't sound like anything is happening because we don't have that ability to perceive it in our ears, and yet dogs do. And so really what is happening in a sound wave is that you get a series of what we call compressions and rarefactions that travel from your source of your wave. Let's look at what these things are. So we get back to our slinky and wave compression that's happening here. If you remember from before, this is a longitudinal wave. It's moving back and forth. And this is a good visualization of what's happening in a sound wave. So when you look at a sound wave from any source, it is starting some kind of a vibration. So it's pushing or pulling air. So this direction here, if you push it, is called compression. If you're kind of pulling it back, it's called rarefaction. But either way, it's creating a change in the pressure of air, the amount of air in that spot, and that then ripples through the neighboring air particles all the way through space at many hundreds of times per second. So a good example of this is in my house, and I know that in some of yours too, you probably have seen this, is that when you have a small little entryway, or even a room that just has one window, it's easy to see this. If you open and close a door in this small entryway, and you look and see what the other door or window does. So for example, if you were to quickly open a door in this situation, so you see this person is pushing, it's compressing the air particles this direction, and then that kind of travels all the way through and pushes the drapes out here. So you can see it kind of makes a little breeze to flow out the window. When you close the door, so in that time you're really drawing air back this way, and that leaves a small little bit of, sorry about that, a small little bit of a vacuum right here. And so what's going to happen is that these air particles are going to fill in that space, and they are going to pull air back in. So it's kind of like a little mini vacuum that's taking place, this change of pressure between both of those different situations. And these two things, again, are called compression, pushing in, rarefaction, when that's being kind of pulled out, or low pressure. So for this wave motion, like others, it's not the medium itself that travels. The air is moving slightly in its kind of region around it. But ultimately, what's traveling from your ear to, or your mouth to somebody else's ears, is not an individual set of particles, but the wave of energy as it's transferred from one molecule to the next. So it's the pulse of energy that travels, not the material itself. Same thing in a wave. If you throw a rock in the middle of a pond, you see that ripple moving out from there. It is traveling, and there is energy moving, but overall the amount of water that's moving from one point to the other is very, very small. It's only shifting back and forth, or in the case of the water, is moving up and down. And so this gives a nice visualization of this same thing taking place. These little purple dots here indicating the air particles themselves. And so if sound was traveling down here, it pushes some of these together, and then that causes, as it pushes down here, causes areas of low pressure right here and areas of high pressure right here. And this is would be my sound wave. Okay, so it wasn't supposed to get bigger, but you get the idea. And so different medium can transmit sound. So it has to travel through some kind of media, some kind of object that transmit it. So solids, liquids, or gases. Oops. And the speed of sound will then change depending on that. If you've ever been inside of a pool or something underwater, you can hear sound travel from the very far end of the pool, whereas if you were just sitting on the side of the pool, would not be able to hear that. Or something that they use sometimes in movies with trains is someone will put their ear down to the metal in the tracks, and that is true that that sound can travel very far via a piece of metal than it would in the air. Now it's not going to be super loud, but you're going to be able to tell that as it travels through those different media. So when you look at the speed of sound, you kind of have to ask the question, in what? And so usually we talk about the speed of sound in dry air, which is listed at about 330 meters per second. So that means then that sound cannot travel in a vacuum. It does not work if you have nothing there to be able to, any molecules to be able to push or to pull back, or the compression rarefaction that needs to take place for that sound wave to travel. So I put a couple of links. One is actually a link from the movie Interstellar, where you see this take place and why they film it that way. There's obviously the music in the background, but in terms of the actual event that takes place in space, you don't hear it. There's no sound to it. It's kind of, you notice it because you're used to seeing those things happen with a big explosion or something like that. And the other one is an example of what we see right here, this little animation from your book, is you see a bell jar with, which was originally given its name because it was given to demonstrate what happens to sound in a jar that the air has been evacuated. So there's a link to there as well. You can check out those two things. Right. So we learned for today is that sound is a wave of pressure changed through some medium, air, water, metal, etc. The frequency of the sound is what we sense as the pitch. So the higher the frequency, the higher the sound pitch, and it can get beyond what we can even hear, and then way lower than what we can hear as well. And sound must travel through a medium, and the medium will determine its speed. So dry air is 330 meters per second. As temperature changes, as moisture changes, that will slightly vary, or if it's traveling through water. But sound needs to have a medium in order for it to work. All right, you can go ahead and work on the rest of your reading or get started on some homework in the rest of our time here today.